All right, so before we continue on to error detection and framing in some of the early parts of the data link layer, I want to cover the relationship between the speed of light, frequency, and wavelength. So the speed of light for this class is close enough anyway, is 3 times 10 to the 8th meters per second. We represent that as C, as common. And so then the wavelength we're going to represent as lambda and frequency. So that is the formula. So as frequency goes up, what happens to wavelength? It gets smaller, right? And then vice versa, right? As wavelength gets larger, frequency goes down, right? Because the speed of light is constant. So that doesn't mean that the propagation of the speed of light is constant through materials. So while the speed of light is a hard-coded constant, it turns out that as it goes through materials, it actually propagates slower than what you would think. And so in general, in this class, we'll use air, space, and other things like that as just the speed of light. And then anything that has like a wire medium or fiber, we'll just use 2/3 the speed of light. And that's roughly about what it is. So, however, this actually gets a lot more complicated than you think. Because if I say, hey, I want to give you, you have a certain bandwidth that's been allocated to you, right, in this particular spectrum. So if I give you that, if you like look at the FCC spectrum, right, it's all divided up in bands. And usually that is bands that are represented in frequency. So like let's look at like FM radio, which is like 88 megahertz to I think it's 106 megahertz, right? Which is allocated to FM radio, right? So let's just take an examination of what that looks like in bandwidth. So if we looked at that as 88 megahertz, right? So that means that the frequency is oscillating at 88 megahertz while traveling at the speed of light. So the wavelength is longer, right? But as we get close to that 106, this is probably over exaggerated, but it gets shorter. Right? Now imagine, so that's megahertz, so imagine what if we go to 2.4 gigahertz for Wi-Fi or 5 gigahertz for Wi-Fi. So now let's say, hey, we are going to take a delta between, we're going to take a subband of this. So we get allocated a channel inside of here for like 98.1 classic rock, right? So 98.1 is actually, I can't remember if it's like 98.1 to 98.2. Can't remember. But anyway, there's a bandwidth in there that you can use. So if we have another channel that is, let's say 102.1. Do these guys have the same bandwidth? Why? So this has 0.1 megahertz, right? And this has 0.1 megahertz, right? So do they have the same bandwidth? Why do you think not?
Well, you said bandwidth was the measure, was an electrical engineering term in terms of length, right?
So bandwidth is an electrical engineering term in terms of oscillation. So they do have the same bandwidth, right? The deal is that the distance from 98.1 to 98.2 is longer than the distance from 90. So you're on the right track. There is something wrong here, right? So while they have the same bandwidth, 0.1 megahertz to 0.1 megahertz, the distance from 98.1 to 98.2 is longer than the distance from 101 or 102.1 to 102.2. And that's because the distance is measured here, right? So this, let's just say this is the delta 98, right? And then 102 somewhere over here. So they have the same. Now, conversely, I give you something in microns. I give you a wavelength or a color, right? That has to do with a wavelength and not the frequency, right? So if I say, hey, at 102.1, I'm going to give you a frequency of 102.1, I'm going to give you 0.1 micron. So now there needs to be some conversions that need to go on. So first you would have to figure out, well, what is the length at 102.1? So what is the length at 102.1? Somebody's got to break that calculator out for me. So it's 3 times 10 to the 8th equals what? 102.1, right? Times megahertz, right? Times 10 to the 6th. Right? Yeah. So if we want to figure out, times the wavelength. We already had that. So if we want to find out the wavelength, right? So that would be 3 times 10 to the 8th over 1 times 0 to 1 times 10 to the 8th. So it's 3 over 101.012 or 021. Right? And then we'd have a wavelength. Conversely, if with 98.1, it would be 3 times 10 to the 8th over 9.81 times 10 to the 7th. So our wavelengths are certainly different. Now, if I was going to give a 0.1 micron of wavelength, right, then that actually would be a different bandwidth, right? So ignoring this back here and ignoring this, if I started out with 102.1 and I was going to give you 0.1 micron from there, there's some questions that you need to ask yourself. One is that 0.1 micron this direction, or is it this direction? It will make a difference for how much bandwidth you have. Why? Why does it make a difference? Let's take our over-exaggerated color chart here, wavelengths. Right, so if I was going to take, let's say for instance this was 10 microns. And then the same length here, 10 microns. Right? There's a lot less waveforms on this side than there are on this side. So Nyquist says that we can only do 2 samples per waveform, right? And so intuitively you should understand that you have more bandwidth on this side. So it becomes important if you have a question, is it 10 microns below, is it 10 microns above, or is it straddling 10 microns? Because all they're going to come out with, in some cases, fairly radical different answers. So those are considerations you should have. So let's take this in a real world example. So let's say you have an allocated bandwidth at 1 micron. And you need to send 6 gigabits per second over this 1 micron. So we have several problems here. One, we have gigabits per second represented as a computer science number, right? As a computer science bandwidth. And we're going to need to translate that into an electrical engineering bandwidth, right? So we would need some other information. What other information do we need? If we got 6 gigabits of bandwidth, what other information do we need to translate that into what? What?
How far we need to translate?
Not yet. Not yet. Let's just say we're just going to stuff information like a TV signal. We're not going to get real world bandwidth yet. We're just going to stuff 6 gigabits of information and send it to Mars, right? And that includes all the encoding and everything else that we would have to do to build that signal, right? So 6 gigabits per second or 1 microns. So in order to get from 6 megabits per second to which is a computer science bandwidth, to an electrical engineering bandwidth, right? We need to know what? We need to know how much data we can stick in a waveform. How much data per hertz?
Sampling rate?
So we would need a sampling rate. We would need a sampling rate. What's the maximum sampling rate? Theoretical maximum sampling rate. It's given by Nyquist.
2
It's
per waveform.
2 per waveform, right? So let's just, for argument's sake, say that's what we're going to do, right? So we have now a sampling of 2 bits per hertz. What else do we need to know? So we have sampling. We also need to know levels per sample, right? So if we can have an infinite number of levels per sample, then we technically don't need any wavelength at all. We can send all our information with no bandwidth, right? So, and so remember, levels were like, okay, we have our bits that we're going to send across, right? Theoretical maximum is this, which is 10101. It's a random string of zeros, or a repeating string of 10. Right, but we could also have levels, right? So we could have, instead of 10, right, we could also have vary the amplitude or something else and have more than one level, so that this becomes 1, 0. This actually becomes 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, right? Yes. Right, and we don't need this one. Where we have 0, 1, 2, and 3. Right, we have 4 levels. And if we have 4 levels, we can send 2 bits. If we have 8 levels, we can send 3 bits. Right, we just take the log 2 of the number of levels halves, and then we take the floor of that, and that tells us how many bits that we can send across at once. But for this example, let's just say we only have 0 and 1, right? Our normal 2 levels, right? So if we not have any extra levels, because we're going to send this thing to Mars, and we're going to assume there's going to be lots of noise when we do it, right? So now we can send basically 2 bits per second, right? And so we take 6 gigabits per second and we can translate that into hertz, right? Which happens to be 3 gigahertz, right? We need 3 gigahertz of electrical engineering bandwidth to send our computer science 6 gigabits per second. So we need 3 gigahertz. Problem now is I told you we're at 1 micron. Right? So we would need to find out, well, what is the frequency at 1 micron? What's the frequency at 1 micron? What's the equation? Our equation is speed of light times frequency and wavelength, right? So that is 3 times 10 to the 8th, and our we don't know the frequency, that's what we're trying to figure out. And so it's F, and what's 1 micron?
One times 10 to the negative 6.
1 times 10 to the negative 6. Okay, so what is frequency? Here. It's 3 times 10 to the 8th divided by 1 times 10 to the negative 6. Right? And so frequency becomes 3 times 10 to the 14th. And 3 times 10 to the 14th is what? It's like 30,000 gigahertz, right? So now we have 30,000 gigahertz. That is correct, right? Gig is 9. So yeah, 30,000 gigahertz, right? And so now this becomes a question of do we go below or above, right? So we need 3 gigahertz of space, right? So let's just do the first one. 30,000 plus 3, right? So now you have 30,003 gigahertz, and so your range is this. Now, if I go to from 30,000 to 30,003 gigahertz, is my bandwidth, my wavelength getting smaller or bigger? It's getting smaller, right? So that means that at 1 micron, we're going to have something that's less than 1 micron, right? So now, in order to find out what to go back to micron, we simply just do the equation in reverse, right? So we take 30,003 gigahertz, and we now figure out what the wavelength is in that, right? And it's going to be something really small. My guess is like 0.9, maybe 99. You do the math, right? And you'll end up with something. You can go ahead and do the math. But then now you have your answer. This is very much like one of the homework questions. It might be very much like one of the test questions that many people will get wrong anyway. Go ahead.
So is the question whether or not we want to go above or below?
Yeah, well, so here's the deal. If I say that your bandwidth is between 1 micron and 2 microns, right, then obviously you're going to have to subtract. Rather than if it is, 0.9 microns to 1 micron, and I want you to start at 1, then obviously you're going to add. It's counterintuitive because...
Oh, because you're trying to get the micron that you're...
Yeah, so how much bandwidth, if the answer is supposed to be in a wavelength, like, right? But if the answer, for instance, was how much bandwidth and frequency, right, then you'd just be done here. All right. So before we get, let's talk about framing. So far, all we've talked about is sending bits over a wire, right? Even in the example we just did, I said, we're not dealing with any encoding, right? This is a finished package. We're going to send 6 gigabits per second. We're going to send it to Mars, so we don't have to deal with any returning of information, right, which is going to become extremely important. We don't have to deal with any of this other networking architecture. So let's start moving up that networking architecture block. We can send a string of bits. The problem with sending a string of bits is that if you're listening to a string of bits, how do you find out where the beginning of some information is? Information consists of boundaries, right? If you saw a string of bits out on just written down on a piece of paper or through a hex header on a screen, how do you interpret what those bits mean? How would you go about doing it? String of bits. What's the first problem?
Where do you start?
Where do you start? Right? Even just to turn that bits to bytes, right, there is 8 different possibilities in that string of bits. So if you were presented with a random string of bits and you're going to do some analysis, you'd have to say, okay, I'm going to shift my boundary 8 different times and look at the information and see what information makes sense. Right? Obviously, we can't do that in a network. Network has to work at line speed. If the network has to work at line speed, we can't do all this crazy analysis on top of it to try to figure it out, right? We need to build something in that can figure it out. So I've already discussed one way is if you have extra signal levels, right? You can say, wow, that's a frame boundary. You could do that. And some networks do in fact do that. It's one of the reasons the physical layer and the data link layer are almost always implemented together, even though they're supposed to have some abstraction. They're almost always implemented together because you can get extra information out of your physical layer. Also consider, like, we want to send this data over, right? And remember, we use waveforms to approximate that. And we say this is like the 0-1 boundary. Right? So what if we had something that was like really noisy? Well, we might end up with a problem over, not too bad, right? But let's say this messes up in there. The physical layer, if you have access to the physical layer, you can actually evaluate how much of a 1 was that 1 and how much of a 0 was that 0, right? You can have proportional bits. You can say, all right, well, this was 30% 1 and 60% 0. And if you have access to that information, then you can make an intelligent decision. So this might be an error because like, for instance, let's say that this was really messed up here, and you had 55 and 45. So it gets reported as a 1, when in fact it was a 0, but it was a really weak 1. Does that make sense? It was a really weak bit. So you might be able to use that, and networks do. You might be able to use that information in the data link layer to correct errors. Because if you had an error correction scheme that could look at, if you had a possibility of an error here where this was 100% 1, right, and a possibility of error here where this was 55% 1, then you can make an intelligent decision and say, well, it was probably the one that was 55. Right? So data link layer and the physical layer are often implemented together. So that is one way we can do it, is use the physical layer. But let's say we're going to be purists about our network and we're going to have a real actual abstraction between our physical network and our data link layer. So we can't use any information. How do we go about determining what's a string of bits? Think back to nasty data structures classes, right? You're going to build a dynamic data structure. How do you do that? Right? You put pointers in. So let's think of a very simple flat data structure. So I'm going to have very simple flat data structure. This part's compressed here. So I have a header, and then I have maybe a footer, and this is my real information here, and maybe I also have like the secondary information, right? So MP3 file. So tiny little header, and then a pointer that points to here for the album information, pointer that points to there for the streaming information, and then the streaming information actually has a string of pointers in it, right? To point to the next block. Now some of these are just, there's not like a memory pointer like you would think of like in programming, right? This is just offsets inside the file. So we could do that inside a network stream. So we have a network stream. And I'm going to represent the network stream as bytes this time rather than bits. So we could sit inside of here and we could say, failing miserably. All right, so we just have a string of bytes. And let's say that we know, because we just booted our system, that this is the first one. Well, when you're building that flat data structure for a file model, you can normally you put a integer in, which represents size, right? And then you can use that integer to jump to the next beginning of the next data. You put an integer there, it represents size, right? And so, like, let's say that we do the same thing here. So this represents size, right? So then it becomes 1, 2, 3, 4, 5, right? And this represents size. 1, 2, 3, 4. And this represents size. 1, 2, and this represents size 1. Right? So we could do that. What is the problem here?
When does it end?
Well, ideally, if everything works fine, it doesn't matter if it ends, right? Because your data becomes, so this is the size, and then your data becomes this, right? And this is the size, so your data becomes this. This is the size, so your data is just at 5, and this is maybe just a heartbeat, right? Actually, this should just not do anything. Right? This will go on. Can't have 0 there. The problem is what happens if you have an error in your network? And the error happens to land here. More realistic would be like a 6. 4 gets translated as 6. Right? That's a realistic error. Right? That is a 1-bit flip. right? The 2-bit just gets flipped. And now you have 4, or you have 6, right? So now, you instead of landing there, you land here, right? And things get all out of whack. And now you're jumping around because everything in a bit stream is a real number, right? So you're just jumping around. If you had your network designed like this, what would you have to do to fix it? You got the first error. What would you have to do to fix it? So on your computer, if it was a file, you would get file corrupted. Right? You might be able to read the first part of the information, but it's file corrupted after that. Right? And then you'd have to go back to like some kind of analysis to fix that file. Right? But if you're a regular user, the file is just done. It's worthless. Right? Because you have one single bit flip in there. You have to turn off the network and start again. You have to reboot your network. So imagine that the internet had been designed like this. The first error that entered the network, you would have to turn the internet off and reset it. So this is probably not a valid way to do a network. What's another idea?
Like we did the other day, check it. You got check every bit or every byte.
Yeah, so we could do error detection and error correction, right? But error detection and error correction only works if you have clear boundaries. So something else.
You set like a start bit and an end bit that don't enter that, what number they're.
Oh, yes. So remember back to other simple data structures, right? We use sentinel characters. So we use characters inside of the data stream that can never be data. Well, there are going to be data, but we're going to figure out how to get past that. So we'll use a sentinel character. So I'm going to use, instead of using half bytes this time, we use full bytes. And I'm going to say our sentinel character is, well, let's talk about this. What would be bad choices for our sentinel characters? Well, we're going to have to use it. It's going to be a byte. Let's just say that the sentinel character is going to be a byte, right? So it's going to be a number. But what are the worst numbers to use?
All zero.
All zero. Why?
Because errors come in bursts. So
Errors come in bursts, right? So all zeros would be bad. What else would be bad?
all ones.
All ones. So all zeros and all ones would both be bad because errors come in bursts. And also, most data is zeros. There's a disproportionate number of zeros in data. So zero is a bad choice for two reasons. Also, data also frequently contains large strings of ones, which would be an FF. Mainly because FF is normally used for file sentinel characters. Right? If you look at an ASCII table, look at what FF is. In an ASCII table, what is FF? I believe it is into file. Huh?
I was going to guess the start of the
Start a file.
So,
I believe it's a special it's into file, right? So we would not want to use 00 and we'd not want to use FF. So we're going to pick two because these are actually used. I'm going to pick our sentinel character as 7E. And then let's look at our data. So 7E is start, right? Seven E is end. And then we put data in the problem in the middle. What's the problem now?
I do know if you started or ended.
Huh? Oh yeah, that's a good one too. We'll talk about that. But there's a more immediate problem. right? There's only 256 bytes. Is there likely to be 7 E's in our data? Right, there's only 256. There's likely to be there, right? So the problem is, what if our data contains 7E? Huh? We're going to end prematurely, right? So what do we do now? Huh? Let's make another special character. Let's make a special character called 7D. And we're going to use that special character, and this seems like we're just building a never-ending problem, right? So we're going to build a never-ending problem for right now, but just bear with me. We're going to create another special character called 7D, and that is escape. So that means that anytime you have 7E in data, right, before it, you're going to put a 7D. Any other problems here?
What if your last character is 70?
Yeah. That is a definite possibility. We're going to send trillions of packets across the internet. Likely, this is going to show up at some time. You know, if it was just random data, it would show up every 65,000 times or so. Right, because it's just the probability of 2 bytes being together. Right, so we have another problem. So now I'm going to make another rule that if 7D ever shows up in data, we're going to escape it with 7D. Is there any problems now?
Same issue.
Is there? So imagine we're reading this in. So we're reading it in, it's coming in this direction, right? So we encounter 7E first, right? And we say, hey, that's flagged, that's the beginning of data. And then this is 1, 2, and then we encounter 7D, right? So we say, oh, that's an escape. What is the next character? 7E. So we drop 7D and read 7E as the next character. And then we get 3, 4, and then we encounter 7D, right? What is the next character? 7D, right? So we kill this 7D and we read this one, right? And then we, since this is, we know this is data because we just read the previous 7D, we read 7E and this is a flag. It always works. If you have an even number of 7Ds, then it is an escape flag. But the real problem is here is, let's look at what we want to do. We want to encode 7D, we want to encode 7E, and we want to encode 7D, 7E, and 7D, 7D. Like, these are boundary cases. These are the problems. Everything else we can work out, right? So it's just normal data. These are boundary problems. So if we're going to encode 7D, we encode that as 7D, 7D, right? If we're going to encode 7E, it's 7D, 7E. If we're going to encode this, what would it be? 7D, 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 7E, right? And then 7D, 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 7D. Now imagine that we don't know what these are. We're going to decode these, right? We run into 7D in the data, right? So we say, hey, this is an escape character. We do a forward look ahead and say, what's the next character? That's 7D, that is data. And we encounter 7D again, that's an escape character. We do a forward look ahead and encounter 7E, and that is data also. In this one, when we're doing that, we're getting rid of the introduced characters. So we counter 7D, we do a forward look ahead at 7D, get rid of that one. And then the next one is the 7D again, right? So we're going to get rid of that one and do a forward look ahead. And then the same thing with this one. It works. Seems crazy, but it works. Now we can determine what's a real flag and what's not. So we can determine framing. In the real world, these characters are actually used in Sonnet. The only additional step is they would really not like to have flags inside of data ever. So how do you get rid of flags in data ever?
Code it as something else.
Huh?
Like go to the data, find all the flags and code it as something else.
Yeah, you do the exact same thing that we did here. Right? So we're going to introduce an escape. Escape you will find in data. And then the next thing, we're going to XOR it with 20. So if we XOR it for 20, 7E becomes 5E. And 7D becomes 7E. Or 5D. If you XOR it with 20. And it's really just a bit flip. If you XOR it with 20, you're simply flipping the 6th bit. So 7 changes to 5. That's it. So now, if you encode this, right, the same thing as above. When you encode it, right, you get a 7D and then a 5D. And then this one you get a 7D and then a 5E. This one you get a 7D, 5D, 7D, 5E. And this one would be 7D, 5D, 7D, 5D. So this now, every time you encounter a 7D, it has to be an escape character, and you will also, the second benefit is you will never encounter a flag in data. So the moment that you encounter a flag, that's it. That's the boundary of the frame. So now we can do frame. And this is actually, not that you need to know this, but this is actually used in Sonnet, which is the point-to-point protocol in Sonnet, which is like the backbone of the internet. So now we got frames. Of course, we could have errors, right? What if happened to be that on this thing right here, since we're now got a fast and loose protocol, right? We can now get a very certain bit flip again and turn that back into a 7E and end up with a flag, right? So let's talk about error detection and error correction. So we talked about it. We want to do error correction, and we talked about duplicating bits, and we talked about why that wasn't such a great idea. But let's actually get into the theory of why that's not such a great idea. So now, remember what code words were, right? We talked about it a lot on Monday. A code word is a set of bits that represent a different set of bits, right? And so let's do a very simple code word where 0 is translated to 0, 0, 0, and 1 is translated to 1, 1, 1. And then we send these across the wire, right? So we're going to send 0, if we're going to send, let's say 1, 0, 1, right? So across the wire would be 1, 1, 1, 0, 0, 0, 1, 1, 1. We have triple redundancy. We're now using 2/3 of our bandwidth to send information across for redundancy. Right? So let's take an analysis of this very simple code and see how good is it.
Horrible.
Huh?
It's horrible because you use ones and zeros in bursts.
It's horrible because we use bursts, right? But just regarding burstiness, right? Let's take an analysis and see. We have framing, right? So we know we're not going to get any mixture of these. So we can pull these off the wire like this. So what if we have a bit flip here? Intuitively, what can you tell me about that?
Odds are it's a 1.
Odds are it's a 1, right? Odds are this is probably a 1. What else?
The other two are 0.
Huh?
The other two ones are 0, boundary.
Yeah, we have ones on the boundary, but we can get boundaries just from the clock, right? And we have framing, so we have real boundaries. What else? What else? How many errors can this thing detect?
Up to 2.
Up to 2, right? So let's say that we had 2 errors here, right? So it can detect 2, and we can, because this is probably a 1, right? We can correct up to 1. Right? Anything above that, all bets are off. Like bursty errors. Right? But we can correct up to 1. Can we correct up to 2? No, because it goes the other way, right? So in this case, we would choose this to be 0, and we would be wrong. Right? So intuitively, we can detect or correct up to 1, and we can detect up to 2 errors. So this is actually the Hamming distance, which I sort of explained terribly last week. The Hamming distance, Hamming said that we can detect if you have data the Hamming distance is the distance to be able to translate one valid code word into another. So we have the valid code word 0, 0, 0 and 1, 1, 1. How many bit flips do we have to translate from one code word to the other? 3. So our Hamming distance is 3. Because that is the number of bit flips it takes to transfer a valid code word into another valid code word. So our Hamming distance is 3. So we can actually derive some general things about this. For error detection, so for any Hamming distance, in this case 3, and this is error detection. We can detect D errors plus 1. So D plus 1 equals the Hamming distance. We can detect any D errors, up to. We can design really bad things, but this is the maximum. For correction, for any distance, we can detect up to 2D errors plus 1. And obviously, if you solve this, right, to detect would be equals distance minus 1. And to correct equals distance minus 1 over 2. And we can never get any better than that. So just like Nyquist and Shannon, these are theoretical maximums. We can't get any better. So let's talk about maybe some implementations of this. We talked about parity. Let's go over that again real quick. Parity is actually not used in practice in networks, it is used in memory.
What'd you say, Nyquist and what?
Shannon. So remember, Nyquist is that you can have 2 samples per waveform, and Shannon was took Nyquist and actually incorporated noise to tell you what your maximum bandwidth, theoretical maximum bandwidth, can get over with the signal and noise ratio. So let's do parity. We're going to send the code word 101, 101. Right? And parity is simply the sum modulo 2 or the XOR, however you want to think about it. They're the same thing of all of this, right? So one XOR 0 is 1. That XORed with 1 is 0. That XORed with 1 is 1. That XORed with 0 is 1. And that XORed with 1 is 0, right? Yes. So just, it's even at 0. So parity. Simple error correction scheme. So what is our Hamming distance? Right? So let's think about this. This is our data. Right? So anything, any 6 bits in a row is a valid code word, right? And so we add, or a valid data, and so we add a 0, right? So if we looked at this in our data distribution scheme, it's half. So these are data plus your parity bit, your single parity bit that are valid. And then this is data plus your single parity bit that's invalid. So our Hamming distance on this is 2. Hamming distance is 2. Right, because I could take this and do 2 bit flips, and it becomes another valid code word. Right? Hamming distance is the number of bit flips it takes to make one valid code word another valid code word. This is valid as an even number of ones, not the same. Right? So Hamming distance is 2. So with a Hamming distance of 2, how many errors can we detect? 1. How many errors can we correct? None, right? Any other thing? Would this be really susceptible to bursty errors? Yes. Probably going to have big problems with bursty errors. Anything else? So one interesting property of parity is that it can detect any odd number of errors. Boundless odd number of errors. So, but other than that, it's pretty crappy. So let's move on to another one. Let's move on to checksums. Who meant it was checksums? Checksums. These are actually used in the internet, right? We're going to actually do an example, if we have enough time, of an IP checksum. If not, we'll do it on Monday. Because I really want you guys to get this. So checksum is we have a number of data, right? And we divide this data up into blocks, and then we append some other data to that represents the digest of those blocks, or in this case, the sum of those blocks. So for IP checksum, this here is 1,500 bytes, and this is 16 bytes. It gives you stronger protection than parity. One is because you have 16 different bytes that are summing things up, right? Let's actually go through and do it. We're not going to do the 1,500 bytes because that will take a long time, and we should probably write a program for that. But let's do 4 blocks of 16, and we'll add them together. So the definition of an internet checksum is defined as the one's complement sum of all of the blocks. So we take a number of blocks. In this case, we're going to do 4, but it will be n number of blocks. You sum those up in 16 byte increments. And do you do that with one's complement, which rotates, and then at the end you take the inversion of that. So let's actually, it sounds really bad, it's actually, this one's pretty easy to do. So let's take 0, 0, 0, 1, and let's do F2, 0, 3, and F4, F5, and F6, F7. Now we're only doing 2 bytes here, not 16 bytes, and we're also not doing the 1,500 bytes string that's actually in IP. But the math is exactly the same. So we're going to sum all of these together. And I'm going to leave a box right here because this is where we're going to stick our checksum in our packet. So we're going to sum them all together. So 1, 3, 5, and 7 is what? $16, which is 0. We carry the 1, right? F, F, and 1. It's F. Carry the 1. Oops, actually, I want. Carry the 1. 13, which is D. Carry the 1. 3 F's and a 1. It's actually 2D. So we have 2DDF0. So, but we have an overflow. So we're going to take this 2 and add it to this number again. So it's DDF0 plus 2. So DDF2. So we now have a sum. Internet checksum goes one step further and it says at the end you have to invert it before you stick it in the bounds. So let's invert it. What's the inversion of 2? So 2 is 0, 1, 0, 0, 0, 0, 0, 0, right? That is 2. I picked these numbers because they're easy. So 2 is this. If we invert it, it becomes what? 1, 1, 1, 1, 1, 1, 0, 1. D becomes D. What's the inversion of F? 0. The inversion of D? 2. The inversion of D? 2. So now we have 220D, and we're going to stick that in there. $220D, and we send that off. Now it arrives at the other side. It arrives at the other side. We're going to check to see if it's right. We do the exact same thing, right? So let's add them all together. Should have left that up there, right? This used to be 2, I believe, right? But so 0. This was 0, right? So it used to be 0, and then now we're adding a D, so it's D, right? But we're carrying a 1. We have FF and 1 again, which is F, right? And then we have 10, 13, and 2. F. We carry the...
You don't need to carry.
No, we don't need to carry. Yeah. And then FFF and 2. F. With a carry to 2, right? So we do the exact same thing. We bring this 2 down here, and we get what? And then we invert it, and we get what? No error. So let's examine this code. If we change one of these blocks, what happens to our sum? Can we make a single bit change in this thing and make it valid? No. No. Can we make a 2-bit change and make it valid?
Yes.
Yes, in very particular circumstances, right? If I make a 2-bit change, it can't be in the same block. So, like, let's say I change a bit here, and if I change 1 bit in the right place, I can make this 7 a 5, right? Then I would need to make a change right here to make this 5 a 7, and voila, the code works. But so it still only has a Hamming distance of 2. But it has better properties than parity, because the bits can't be flipped they need to be flipped in very certain places. And this is the problem with the sum. Basically what I did here is I subtracted 2 out of this by changing a single bit, and I added 2 out of this by changing a single bit. And of course the sum, that's the way sums work, right? If I take a bit away, but I put a bit back somewhere else, then it's possible that it's going to work out, right? Because it's a sum. But it's better than parity because remember, in the real IP checksum, we're doing 16 bytes. First, well, maybe it is only 16 bits. So we're doing 16 bits. So, which is what this is, 16 bits. So that means that it can detect all burst errors up to 16 bits long. Because if I had a burst, let's say these are all in a row, and I had a burst error here that changes all this to zeros, right? And then and it continues on to here, change this to zeros. Then, so long as it doesn't overlap, I'm good to go. So it can detect all burst errors up to 16 bits. It can also detect random data for valid code words up to a probability of 2 to the 16th, because it's 16 bits long, right? Where parity could only do 2 to the 2nd. Random data in parity could have been, if you spit out random data, there's a half chance it's a valid code word, right? Because it's that 1 bit that you can just flip at the end. So in this one, if you spit out random data, the probability that it's valid is 1 and 2 to the 16th. So this is actually used in TCP, IP, Ethernet, I believe, but it's still pretty weak. Why would we have used something that was still pretty weak and still be alive in the internet today?
Fast.
Because it's fast. What is the fastest operation on a computer?
Next one?
Huh?
Next one?
So XOR, addition, and subtraction, which is basically the same thing, right? In any inversions, right? So knots, right? Anything that's simple bit manipulation is super fast, right? The fastest is XORing something with itself because you don't have to load anything more than one register, right? But if you have 2 different values and you have 2 registers, then those 4 things are usually 1 clock cycle. It's really, really fast. So that's why it's used, right? Remember back when the internet was, TCP/IP was started up in 1969, I believe, was when TCP/IP started being deployed, right? Computers were really, really slow. And when we talk about computers, it's not just endpoints, it's not PCs, it's all the routers that were in between, right? They're all computing devices and they're all slow. So that was why we did that. Newer networks like Wi-Fi use CRC, which we will talk about on Monday. CRC, in your mind, is actually division, because we're going to divide it out with long division and everything, but in a computer it's actually not that. It's not real division. It doesn't actually use the division operator. So we'll go through how CRC works, and that will take care of error correction, or error detection, and then we'll move on to error correction. All right? So I put your homework up on Canvas. I also loaded the video, by the way, which took like 3.5 hours to encode it and get it up to YouTube. So keep that in mind when I'm trying to get these things up, but it's up, and I will do the same thing for this thing.